Okay, I want to demonstrate the difference between a longitudinal or mechanical wave and a transverse wave, such as what is significant in light, the transverse wave, and the longitudinal mechanical wave that is in sound. Now, this is a slinky, okay? It's a slinky. And sound going through the air kind of looks like this, where you see these compressions. You see that compression? Okay? And you can see how the compressions are kind of diffusing, don't you? Well, that's what happens with sound. If I'm in a big stadium, the sound, and I'll show this more on the board, the intensity of the sound will decrease as an inverse square function. So 1 over 1 is 1. 1 over 2 is actually 1 over 4 because it's 2 squared, right? Okay. 1 over 3 squared is 1/9. 1 over 4 is actually 1 over 16th. So it goes 1, 1 over 4, 1 over 9, 1 over 16, 1 over 25, etc. It doesn't just go in a linear fashion. It goes in an inverse square fashion. I'm sorry, not just an indirect fashion, a inverse square function. So this is a longitudinal wave, how sound travels through the air. My sound, I'm making noise. That's a low frequency, right? Or I can go, ah! That's a higher frequency noise. Okay, so what I'm demonstrating is a longitudinal sound wave, this slinky, and you can see you have two things in a mechanical sound wave. You have the compressions, compress, compress, compress. You see it? Mm-hmm. It's kind of disappearing right where my finger is. Those are called compressions. And then between the compressions, you see where it expands? Okay, do you see that? How it expands? The expansion is actually called the rarefaction. Rarefaction. Okay? That's the rarefaction. Okay, now hold Carly without an N is my videographer, along with Laura without an N as well. And this is a transverse wave. If you look at this, see when you think of a wave, you think of this. Okay, where you have peaks and valleys. This is actually a standing wave that Carly without an N and Laura without an N are demonstrating, where there's a point here, right here, where it doesn't really go up or down, does it? It's kind of like between. It goes down, up and down here, and it goes up and down here. But there's a point which kind of stays around, which doesn't really move much. And those areas that don't move much between the waves, peak, valley, peak, valley, peak, valley, okay, peak, valley, etc. Those are called nodes, where you don't have that. And we're going to go outside in the hallway and demonstrate that a little bit better. Anyway, the distance between two waves, again, this is a transverse wave. It's a standing wave, actually. So if you talk about wave mechanics, let's call it a standing wave. But anyway, I'm doing this wave because I want to show you wavelength and trough and crest. Okay, the trough is the lower. Let's say this is the top of the wave. Let's say that's the positive region. That would be the peak, and then this would be the trough. Okay, and the distance between two peaks would be wavelength. Mm-hmm. The distance between two troughs would also be a wavelength, right? And the height of the wave would be the amplitude, right? All right, let's stop, and we're going to go outside in the hallway.